Assalamu alaikum. Good morning. So this is fifth lecture. Last time what we did is we discussed how to write quantum state of a composite system, where we discussed a state of two level systems, 2 qubits, and we discussed the structure of the state and if the state is a product or entangled. And today we will continue along that direction, and we will be discussing, I'll present some use of this entanglement. So basically we can use this entanglement to transfer quantum states, and we call that teleportation. And today that's our main objective. And to know how a quantum state can be teleported, we need a few basic concepts, and these are operations on a single qubit and operations on 2 qubits, etc. So I'll start from there. So what kind of operations we can perform on a single qubit? So qubit here means a simple 2-level system. So 2-level system is a qubit for a quantum bit. Okay, so we know that we can write its state as cos theta by 2, and today I'll be using notation 0 and 1 instead of 1 and 2. Okay, that's more standard for this kind of topics. And so this is the state for 2-level system or qubit. This 0 and 1 are our basis state. On Bloch sphere we can represent that as a state with spherical coordinates theta and phi. So this point on the sphere, it's theta and phi, this state psi. Okay, so now what kind of operations we can perform on this? We discussed the dynamics of a 2-level system as well, okay, in second or third lecture. And what we saw was that if we have a Hamiltonian like this, where we have some number over here, if we have Hamiltonian of this form, then what the dynamics would do is we have this vector B, suppose this B is over here, suppose it's like suppose this is that direction made of those 3 numbers. It can be a magnetic field interacting with a spin half system, or it can be any generic 2-level system, and those numbers could correspond to anything, okay, that makes that Hamiltonian like that. So if we have this vector over here, then this state would revolve around it. Okay, so the dynamics will generate. So on the sphere, it will stay on the sphere, but it will revolve around that. And the frequency with which it would revolve is basically magnitude of this, or bx square bz square. So that's the frequency with which this state would revolve on the Bloch sphere around this direction. Okay, so that's the dynamics. Now, if we start from here and we evolve this system for a time where this omega t is equal to 2 pi, then the system will come back to its original position. Okay, and if we choose, so let's call it theta, we are using theta there, then theta phi, let's call it alpha. So this is a angle, and depending on these two numbers we can choose this product and we can rotate that state around that axis by this angle. Okay, so that's the kind of rotation. Now this is the operation on this state or this qubit. So there can be any, you can think of other operations as well where you change the state of a system. So basically you can choose any transformation. Okay, so the only condition is the transformation needs to be unitary. So you can take any 2 by 2 matrix where u dagger u is equal to 1 and u is a 2 by 2 matrix, unitary matrix, and you operate that, you multiply that matrix with this state, and in these bases this state would be like cos theta by 2 exponential iota phi sin theta by 2. Okay, so you multiply that matrix with this vector and you get another state. So this is a transformation and this is an operation on this state of this qubit, okay, in general. So usually we need some rotations. Okay, yes.
सर ये जो आपने स्फीयर बनाया है इसके ऊपर जो हर एक पॉइंट होगा वो एक तरह से हमें सिस्टम की स्टेट बता रहा है, तो हम ये कह सकते हैं कि ये हमने एक तरह से हिल्बर्ट स्पेस ड्रा की हुई है, लेकिन जो बी है वो हमारे पास एक फिजिकल क्वांटिटी है जो अलग से वेक्टर, जो फिजिकल वेक्टर स्पेस है उसमें एग्जिस्ट करती है, जैसे वो हमारे पास पोजीशन वेक्टर बताएगा जिसमें वो पॉइंट कर रहा है। तो ये बी हम हिल्बर्ट स्पेस के अंदर इस तरह कैसे ड्रा कर सकते हैं, ये मुझे समझ नहीं आया।
हाँ, मैं बताता हूँ। ये जो स्पेस है ये बेसिकली रिप्रेजेंट तो स्टेट स्पेस को करेगा, लेकिन स्टेट स्पेस को सिर्फ ब्लॉक स्फीयर की सरफेस पे पॉइंट्स रिप्रेजेंट करेंगे। बाकी ये 3 कोऑर्डिनेट्स है, बिल्कुल कोऑर्डिनेट स्पेस की तरह, रियल स्पेस की तरह, इसका कोई इशू नहीं है। आप किसी भी वेक्टर को यहाँ पे ड्रा करके उसकी डायरेक्शन रिलेटिव टू दीज एक्सिस आप बता सकते हैं।
सर लेकिन फिर वो जो बी वेक्टर है उसका हम दूसरे जो स्टेट के वेक्टर्स हैं उनके साथ तो रिलेशन हम एंगल इस तरह नहीं बता सकते हैं ना?
कौन सा, ये वाला वेक्टर?
यस सर।
इसका किसी और वेक्टर, कौन से वेक्टर?
सर जो बी वेक्टर है हमारे पास,
ये बी।
यस सर, इसका हम फिर रिलेशन जो उस स्टेट के वेक्टर्स हैं उनके साथ तो फिर नहीं बता सकते आप?
जो स्टेट के वेक्टर्स हैं वो इधर एक पॉइंट को करस्पॉन्ड कर रहे हैं।
यस सर।
उसके अलावा उसका कोई रियल स्पेस के किसी वेक्टर से कोई उसका इंटरप्रिटेशन नहीं है, ठीक है? तो हम उसको कोई ऐसे इंटरप्रेट नहीं कर रहे कि रियल स्पेस में कोई वेक्टर है। रियल स्पेस में वेक्टर नहीं है, ये ब्लॉक स्फीयर है। स्फीयर की सरफेस के पॉइंट्स हिल्बर्ट स्पेस, क्योंकि वो थीटा फाई हैं और थीटा फाई यहाँ पुट करें तो एक स्टेट मिल सकती है, ठीक है? और इन जनरल ये 2 पॉइंट्स कोई भी आर्बिट्रेरी किस्म की सुपरपोजिशन स्टेट बना सकते हैं, तो लिहाजा ये सारे पॉइंट्स मिलके वो सारी आपको स्टेट स्पेस दे रहे हैं। बेसिकली 2 डायमेंशनल स्टेट स्पेस है, ठीक है? 2 कोऑर्डिनेट्स चाहिए आपको।
सर यहाँ पे आपने कहा था कि जो हमारे पास वो पॉइंट है वो उस जो बी का वेक्टर है उसके गिर्द वो रिवॉल्व कर रहे हैं।
हाँ,
तो वो मुझे समझ नहीं आ रहा क्योंकि बी जोन से वो तो उस स्टेट्स में, उस
सही है,
स्पेस में है ही नहीं।
जस्ट चीज़ को प्रेजेंट करने का तरीका है। सो इट्स जस्ट अ वे टू प्रेजेंट हाउ द डायनामिक्स वुड इवॉल्व अ स्टेट। सो इफ यू हैव दिस काइंड ऑफ हैमिल्टोनियन, its dynamics would be like this. So this would be revolving around on the sphere, but so it has a plane, so it's a great circle, it has a plane. So which, I mean, where is the, I mean, how would you determine its direction? There could be any direction. So this direction is the direction for that great circle, for that revolution or circular motion. So just a way to present things.
I can try to explain. So what you have is a linear combination of 0 and 1. 0 and 1 are the basis states of the Hilbert space. They have in front of them complex coefficients. You can call it C1 times 0 plus C2 times 1. These are complex coefficients, which means that there are 4 of them, 4 numbers, constrained by the fact that C1 squared magnitude squared plus C2 magnitude squared is equal to 1. So therefore there will be 3 numbers. Hence it will move on a manifold with 3 coordinates. He has chosen, so you have this satisfying cos squared theta plus sine squared theta equals 1. And there's e to the I phi. But my question is, why did you not take B to be along the z-axis?
Yeah, now I'm going to do that. So that's easier, yes. So let's make things a little simpler, okay? So let's take a specific state instead of general theta phi. Let's take this state 0 plus 1. Suppose this is our state. Okay. On the block sphere, this is pointing along the x direction. So if you measure a component along, if it's a spin, then this would be like eigenstate of Sx with eigenvalue plus 1. Okay. So on the block sphere, this state is like this point along x. Okay, so its Cartesian coordinates would be 1, 0, 0. Now if you take B along z, then that means your B is like that. And now the dynamics for this system would revolve it on this circle in the xy plane. So it would be revolving like this. Okay, so that's a simpler picture. So now if you start with this state and you want to make it eigenstate of y, what you would do is, this is 90 degrees, so you would evolve it for a product of omega and t that corresponds to 90 degree. Okay, so you choose this alpha and you can go anywhere. Okay, so now suppose if you want to start with this and you want to go to an eigenstate of Sz, that means you want to go to 0. So you want to transform this state to a state 0. What kind of transformation would be required? You need axis along y, and then you would be rotating it around that by an angle, again 90 degree. Okay, so you choose B along y and do this for 90 degree, and that would be an operation. So this is kind of how you would do it in experiments, for example with spins or with atoms, two-level atoms. So there are different protocols to do that. So you realize such kind of Hamiltonian for your two-level system and do some operations to change state of your two-level system, a qubit. So I'll be calling this two-level system a qubit. Okay, so you can change your state of qubit with some operation like this. And Now there are infinite possibilities for this, but some more relevant and more useful operations would be like this kind of rotations, where you want to rotate along this, and if you rotate, suppose if you want to rotate along x by 180, that would take this down there and take this up there. Okay, so you would change this to 1 and change 1, which is here, 1 is somewhere here along minus z, and this is 0. Okay, so this is kind of a bit flip. Okay, so the unitary matrix to do that, it's basically this polymatrix. So you operate this onto that state, so you can check it yourself. So there is 0 0 here. Suppose you have 1 0, so this is 1 0, this is 0 1 in this basis, and what you would do is this will be like this, and if you have the other possibility, then it will flip that as well. So this is kind of changing 0 to 1 and 1 to 0. Okay, and similarly what we can do is we can have another unitary transformation where you have this kind of matrix. This is again sigma z, basically polymatrix, and what this would do is it would keep this as it is, but it would flip the phase of the 1. So this would do this. So if it's alpha 0 plus beta 1, then z on, suppose this state is phi, then z on phi will be alpha 0 minus beta 1. Okay, this is another kind of operation. So you can think of many operations. So these two are very important. I will be using that in the teleportation of a quantum state. So there are other operations on 1 qubit as well, so I need one more. So it's like this. So 1 by square root 2 x plus z. So it has its own name. Hadamard. Okay, so this is a transformation, and what it does is it has this kind of structure. What it does is, if you operate this on 0, so you have 0, this will become 0 plus 1, I guess. Let me check that later. And this will become 0 minus 1. And if you operate h again, it will reverse its previous operation, and you'll again get 0 or 1. So for this case, if you apply it 2 times, it's identity. So you can check this if it does this. So this state is 1 0, and this is 0 1. So here this is our state 0. So if you apply this onto that, what you would get is, so 1. I'll multiply this later on. Okay, let's multiply it, and if you multiply this again 1. Okay, so this was 0, and this is this one. So you convert or transform a state from 0 to a superposition like this or that, and this is eigenstate of sigma x. This is eigenstate of sigma again sigma x with eigenvalue -1, and this is again with eigenvalue +1. So but at the moment, just focus on the action of the operator. So you apply some 2 by 2 matrix, unitary matrix onto a state, and it transforms that state in certain way. Yes. अभी बताया आपको ना डायनामिक्स के थ्रू. So you would apply some appropriate field B for your system, and you would know its strength omega, and you would wait for certain time t again depending on your requirements, and it would evolve it to your final state. So experimentally these operations are done via some time evolution or something like that. Okay, it depends on the system. With lasers, for example, usually I think there are other passive elements you put there, like a quarter wave plate and something like that. So you split a beam and then put a quarter wave plate and it does something with it, and you can do operations like that. But with an atom or a spin, a system like that, it's very simple. You just perform this kind of dynamics for certain time, and then you basically perform these operations. So now I'll not be discussing how these operations are realized experimentally in detail, but it's basically time evolution. Okay, so but we will be focusing on the structure of the transformation and what these transformation do to our state. So these three will be needed for our teleportation problem. Okay, these three, and these transformations have a name. Basically they are called quantum gates. So these are quantum gates, just like classical logic gates. These are transformations that apply onto a quantum state. So I mean, they are called quantum gates. So this is X gate, Z gate, and H gate. There are many other gates as well, but I'll be needing just these. Okay, so these are just 2 by 2 transformations. So now we know some transformations and their action. Now let's talk about a transformation on a qubit, on a pair of qubit. So basically, if we have 2 qubits, what kind of transformations we can do with that? So I'll be needing just one. So again, you can think of many things, how a given transformation can be realized experimentally. Again, you would need some kind of interactions that you put in your Hamiltonian. So there are different ways to realize different kind of interactions with different experimental setups. So but you would always need some interactions in your Hamiltonian to perform some operations on a pair of qubit states that I'm going to talk about. So I'll be only needing one 2 qubit operation. So and that is called a C0 gate. So it's a C0 gate, and what it does is, C is for condition or conditional, not is not. So in classical logic gates, what not does is it flips the bit. So it converts 0 to 1 and 1 to 0. And C means conditional. You do this operation conditioned on state of something. And here it's about 2 qubits. So qubit 1 and qubit 2. So qubit 1 would be providing us the condition. Okay, the state of the qubit 1 would be providing us the condition. So this, and the operation will actually be performed on state of qubit 2. So in that sense, it's a 1 qubit operation, but since it's conditioned on state of the other, actually it's 2 qubit. Okay, so here it's an operation, and this qubit that gives us condition, it's called control. Okay, so controlled, so control qubit. So since it gives us the condition, and this is our target qubit where we'll be performing the operation. Okay, so that's the terminology in this case, and there is a way to represent this as well. There are ways to represent those as well. So we have this kind of a line where time flows from left to right. So basically we have initially some state over here, and here we will have some transformed state. So we will have some state psi, and here we have x psi if we have this kind of gate over here. Okay, so in this case, so this is for that, but let's so here we have the two lines for 2 qubits just to represent it, and we usually denote it like this. So this is qubit 1, this is qubit 2, and depending on state of this, it will perform some action on this, and we will get something over here. So these are 2 inputs, these are 2 outputs. Okay, and what's the operation? The operation is simply C naught, and C is if the first qubit is in the state 0, then you do nothing to qubit 2. Okay, then qubit 2 operation on qubit 2 would be identity, and if you write it in the particular 2 qubits Hilbert space, then we can write it like this. So if this is 0, then for first, for second, it's identity. So basically you leave it as it is. But if first qubit is in state 1, then what you would do is you don't do anything with first qubit. What you would do with this is not. So you would flip it. So basically kind of X. Okay. So you flip that. I guess yes. Okay. So that's the actual operation, and it depends on the condition. Okay. And now we can write it as a matrix in 2 qubits Hilbert space. That would be 4 by 4 matrix. So let me do that as well. That would basically summarize the whole information that's in here. So this C naught is basically this. So for first qubit you do nothing. For second qubit you flip it. I think it's like that, but there are other numbers as well, I guess. Let me see if I have written it. No, I haven't written it. You can check that. So in this form, basically it's like this. So 0 0 times you do nothing. Let's call it psi plus something like that. Okay, so this bar means you flip that. If it's 0, stay 0. I'll verify that later maybe. Okay, so just to save time. So now we have these 4 operations, these 4 gates. Okay. Okay, so let's see where we can go from here. Okay, there is one more thing that we need to discuss, and that's about measurement. We can perform measurement in different bases. Okay, we can choose any basis and perform measurement. So, What does that mean? Suppose we have again, let's draw block sphere. And this is E, this is X, this is Y. Okay. Suppose we have a system in state 0. So here. Now that's the state of our system. Now if we perform a measurement in SZ basis, so SZ means sigma Z, basically Z, SZ or sigma Z or Z, whatever you like to call them. If you perform measurement in these bases, what does that mean? When we discuss postulates of measurement, then we discuss that whenever you perform a measurement, the only outcomes can be from the spectrum of your operator. So if you perform measurement of SZ and your state was this, then what you would get? Here, this state is an eigenstate of this, so you can clearly say that, okay, this would give us +1. So suppose its eigenvalue is +1 and its eigenvalue is -1, then you would know that if you have this, you perform measurement of this, then you get +1 as an eigenvalue, and your state would be projected again in the same along the eigenstate of this, so it's the same. So state would be the same. Okay, so that's the eigenvalue, that's your state after the measurement. But if you choose to measure instead of SZ, SX, system is in the same state, 0. If you like to measure SX, what are the possible outcomes? Exactly. So we can compute the probabilities for the outcomes by projecting this onto the eigenstate of this. So first we need to know the eigenstate of this in these bases, then we can easily project these. So eigenstate of this in this basis are these two. So one is with eigenvalue +1, other is with eigenvalue -1, and this +1 is 0 +1 by square root 2 if you normalize them. Now you can talk about probabilities. So if your system is in state 0, then you only have this 1 by square root 2. Okay, so let me probability to be in with +1, and if this is an X basis, so X, that would be this state projected onto this. So and it only picks this part, the other one is 0, so by scaling you get 1 by 2. Similarly for the other, you get probability 1/2. So if your system is in this state and you choose to measure SX, your outcomes are 50-50. So 50% probability with eigenvalue +1, 50% with probability eigenvalue -1. And if you get this one, your state would be projected onto this. And this has this one component as well. Okay, and if your state is projected, if you get eigenvalue this, then your state is projected onto this. So by measuring, by choosing the measurement along another axis, you can change your state to these as well by measurement. Okay, and this is probabilistic. So now to do some generic operations on a qubit, you sometimes need to measure in a general direction. So instead of measuring 0 and SZ, you measure SX or SY or some other direction as well. But the good thing is that this can be avoided by performing some other operations. So with time evolution, you perform some operation and then measure SZ, and then you can know if you had measured SX, you would have gotten this or that. So you can do that the same with measurement of another operator, but you need to do some other. You have to pass your state through some other logic gate to do that as well. Okay, so instead of measurement in different bases, you do some logic operation, you transform your state and then measure in SZ. Okay, so SZ is special in this case. Okay, so because you always like to work with 0 and 1, so this is kind of a little special. So you can avoid measurement in other bases if you transform your state first and then measure this. Okay, so that's the one thing that would be needed, because in the teleportation we can either measure SX or we can perform that suitable operation and then again measure SZ and we can perform those operations. Okay, so but this has some interesting concepts, general quantum mechanics concepts, I guess, that you need to know. So if you have this state, you can measure SX. You are not going to get +1 with probability 1, but probability half. Okay, so that's one thing. So now let's talk about some usual computation. Usually if we have some data on our computer or laptop, we usually copy it from one place to another. We usually put our USB and copy some file from our hard drive to a USB. That's very common. But can we do similar operations with quantum states? That's a question. And you would be amazed to know that it's not possible actually. So you cannot copy quantum states. And so classically, suppose you have a floppy disk or USB and its bits are in 0 state. Okay, and all the bits are in 0 state, and then suppose you just at the moment what you can do is you can copy your data bit by bit. So let's talk about just one bit. So you have your USB bit in state 0 and you plug it with your computer, and your computer's data, it can be either 0 or 1. Okay, that's a classical bit. So it's either 0 or 1. Okay, so that's a classical bit, it's not a qubit. Now how would you copy this? So what you need is you need to decide a certain protocol that can do that. So what's that protocol? It's very simple. What you want to do is you have something over here and you want to translate it to your USB. So this is laptop. This is originally in 0. Here it can be 0 or 1. So what you can do is, if this is in 0, then you need to have this bit in 0 state. So you don't need to do anything actually. So if this is in 0, you don't do it. So the protocol is, if your laptop bit is, let me write it here, if this is 0, you don't do anything. Okay, don't do anything. But so let me call it identity. If this is 1, you need to have this bit flipped because it's originally in 0. So you want to make it 1. So it's easy, you perform some operation and flip it. Okay, so that's how you copy a classical bit. Now usually when you copy a file, you have a string of bits, so you can copy that bit by bit, and you can do that. There's no problem. So that's how you would copy. But in quantum case, again, you can start we would talk about only state of a 1 qubit. So you have your qubit, you can start with the 0 state, there is no problem. And then the thing that you want to copy, now it can be in a superposition of 0 and 1. But let's start with a case where you have either 0 or 1. Okay, so just like classical. So now what we can do is we can, if this is 0, we don't need to do anything, just like this. If this is 1, then we need to flip this. We can do that here. So basically in this case, if we have a state 0, then this was our state, so we want to keep it that way. If it's 1, our qubit is 0, we want to get this, and the same protocol can give us this. Okay, there is no problem. So we can basically copy this kind of state. But if we have a general superposition, okay, then this fails. So if you have a state that you like to copy, it's in alpha times 0 plus beta times 1. Now let's try the same protocol. What we ideally like to get is with an unknown state like that, psi, starting with this, we like to obtain this. Okay, so these are tensor products, if you like to put. This is what we like to copy here, so this is what we desire. Okay, can we do that? That's the question. So using the same operation over there, so we start it like alpha 0 plus beta 1, then this operation, and what this operation is actually is kind of C naught. Okay, so if it's 0, it doesn't do anything. If it's 1, then it flips that. So basically it's C naught. Then what can we do is we get this one. We copied those bits, but we did not copy this state. That's, if you write this, it's like alpha 0 plus beta 1 times alpha 0 plus beta 1. And you can open it and see it's like alpha square 0 0, let me use this shorthand notation, plus alpha beta 0 1 plus beta alpha 1 0 plus beta square 1 1. So we wanted to get this. Yes.
Then next plus beta times 1 0 क्यों नहीं है?
Because control qubit is in state 1, and that's the instruction for C naught, that if this is in 1, you would flip the other one. Otherwise you would not be doing anything. I mean, if you don't change this one, it's again the same state, so that would become identity. Okay, so we wanted to do this. we got this with that kind of operation, and it's clearly different. This is 0 0, so this is basically alpha 0 0 plus beta 1 1, and this is not alpha square, I mean like that even in these two terms. So these two terms, even those are different from this. So but this is clearly not present in here, so these are kind of interference in this, but let's not call that interference. But so these two terms are not here. Here amplitudes are different, so even this, if somehow this were not there, this is different. So this state that we wanted is not equal to what we got from this operation. Now you can think of other operations. I mean, this is one kind of operation to do to try to copy a state, but you can think of other operations, and it turns out that it's not possible for any operation. You cannot think of any operation that would get you here.
Any linear operator?
Yes, linear of course,
Otherwise,
and unitary.
otherwise you
Yes, I mean unphysical, yeah, mathematically, of course you can make a matrix that maybe can get you here, but yes, the conditions are it needs to be unitary. So
problem is that quantum mechanics has to be linear.
yes, the quantum mechanics is linear, yeah. So that's a good thing here. So now if you can't do anything, so it's a theorem. So this theorem says that you can't do this. Okay, so it's a level of a theorem. So you cannot copy a quantum state. It's called no cloning. So cloning is copying exactly. Okay, no cloning theorem. Now apparently it seems something a kind of limitation, but this is the good thing. If you cannot copy a state, then if I am sending you some quantum state using some mechanism, then no party can copy that state. So our information is secure. Okay. So if someone tries to tamper information midway, if I'm sending you, I mean via cable or something, and somebody is tapping that cable to get to our information, then if it's quantum information, then you can't do that. You cannot copy a quantum state. So if you try to copy, you would destroy that state. If you make any measurement on that, you would destroy that. So I mean this destruction is good actually. Okay, so that's the basis for secure quantum communication. This simple thing. Okay, if this were possible, then of course you wouldn't know. I mean, somebody would tap your cable.
So ये सिर्फ टू स्टेट सिस्टम में इस तरह होता है, वन स्टेट सिस्टम अगर हो तो फिर आप क्लोन कर सकते हैं।
One state?
यानी अगर सिर्फ लेट्स से अल्फा 0
Yes, even for two state, if you have these specific states, then you can copy. Okay, if your state is on the poles of the Bloch sphere, then you can copy. Then it's simple. But an arbitrary state theta phi cannot. Okay, so in general you would not be using these two because you know they can be copied, so you would use something else unless somebody knows which two states you are using. Okay, I guess, because if somebody knows your state, that means on the sphere, so basically it's a basis transformation then. So if somebody knows your z axis, which direction you are calling z, okay, then and if you are using 0 and 1, then they can copy this. Okay, now you can use this information, apply it on a superposition state. For superposition state, again, suppose you choose this direction, then this and this, these are your two states, and if someone knows this direction, then they can perform measurement on this state doesn't change, because I mean it's an eigenstate for this axis, so then they can copy. So if someone doesn't know orientation, and there are infinite possibilities, so of course that's not possible as well. Okay, so for an unknown quantum state you cannot copy. If someone knows your state, then they can copy. Okay, but of course the whole purpose of secure communication and tapping to it is copying that, and if you know, you don't need to copy. Yeah, so so that's the good thing about this, about the quantum states. Okay, so just absorb that. And now, what if I like to send my quantum state to some other party, someone? Can I do that? And do I need to send my whole setup? For example, if it's some low temperature setup, some refrigerated setup, and there is some atom or some spin in maybe nitrogen vacancy in diamond. So there are different realizations for your qubit. So it can be a superconducting qubit. It can be oxygen or nitrogen, I think nitrogen vacancy in diamond. So natural crystals, they have different defects, point defects, and some of those defects can have some two-level systems due to spin or something. So nitrogen vacancies in diamond, they are usually used as qubit, and there can be other systems as well. But do I need to send the whole setup to someone if I want to send the state of the system, or can I teleport it? Okay, teleport in usual sense, without sending the physical thing. Can I teleport my quantum state? That's the big question. So I'll tell you how to do that. So that's possible. We can teleport a quantum state. That's quantum teleportation actually. Okay, so with quantum teleportation you cannot teleport yourself to somewhere else. Okay, but you can send state of a quantum system. So recently, yesterday I saw a paper in PRL, Physical Review Letters, and in I think Chinese Normal University, some group sent 100 state of 100 qubits simultaneously. I mean, people have been sending a state of single qubit or multiple qubits sequentially, but they kind of in one single operation they sent a state of 100 qubits. I did not read that, so I don't know how exactly. So, but this is a news. It's in highlights on American Physical Society's website. So,
Tangled state of 100 qubits.
Yes, there needs to be entanglement with, but it's a big thing, I guess.
Do you remember the author?
No, but if you go to APS physics, so on the physics side, they share highlights. So in there, it's on top, I guess. So APS physics. Okay, now how can we send? Here I'll discuss only teleporting a state of single qubit. Okay, and I tell you the required logistics. Okay, and suppose you have a qubit in some state and you want to send it to your friend who can be anywhere on the planet, and just like other parcels, you go to a courier service. Okay, and this courier service is very special. They can send quantum states, and you give your system to them. Okay, this is my system, please teleport it to that address, and this is you go to courier service. So suppose it's DHL or TCS here or whatever. So this is their office. Okay, and your friend lives across the globe, maybe in US or somewhere, and he will pick your parcel from their office. Okay, so this is their office, suppose in New York. He'll pick it from there. This is suppose in Islamabad. Now, you know how usually they send your parcel. So you give them your parcel, usual parcel, suppose clothes or something, and they take it from you. They have a communication channel. They give it to their van guy, and van guy gives it to the airport guy, and airport guy puts it on the plane, and plane goes to that country, and then again some vans can take that to this. So there is this path there. Okay, it can be airplane or something, and whatever. Okay, so that's how usually parcels go from one courier office to another courier office, and your friend picks it from here. He will pick it from here. Okay, what you need to do similar thing with a quantum state. So for that, this courier needs to be very special. So what they need is, so they have these two offices. They need to have a 2-qubit entangled state in, say, one of the Bell state. Okay, we talked about the Bell states, 4 Bell states. They are entangled. So these two offices needs to they need to have 1 qubit each from a Bell state. So they need to share a Bell state. So 1 qubit is in here, other qubit is in there. Okay, so let's say first qubit and second qubit. So these 2 qubits, if they are in Bell state, of course they are entangled. Okay, so that entanglement would allow us to teleport things. So now they need to have this pair of qubits in an entangled state. Okay, that's necessary. That's the resource that's required. Apart from that, they also need to have SMS service or phone. They have phone, yes. They can call each other and they can email each other. So they can call and email each other as well. Okay, so these are 2 things they need to have. If they have this and they know how to do this, then they can do that. Okay, so these are resources, and now you have your qubit. So your qubit is in this state. Let's say it's alpha 0 plus beta 1. Okay, so this is your qubit. You want to teleport this and you want to have it here. Okay, you want to send that state via this machine. You want your friend would get this. Okay, that's the thing. Now how it would be done, that's the question. Okay, so these 2 guys in this office, they know the rules. They know that this guy would know that he will receive a call or text, and that text would have only 2 bits, classical bits. Okay, so those 2 bits can be in 00, 01, 10, 11. So basically these are 4 numbers. So in binary it's 1, 2, 3, 4. Okay, so he will receive a text with a secret code 1. Okay, and he would know that, okay, now I have to do something depending on this guy. Okay, and how this guy would know what code to send. Okay, so he would do something and then he would know, okay, I need to send that guy 0, this one, or that one. So which one he would send? He would perform something, okay, some operations, and do something, and then he would know, okay, I need to send that, and he would call them, okay, 00, that's the code, okay, and then this guy would know that depending on this code, I need to perform something, okay, and then he would perform something and he would get his part of the second qubit in this state, and he would show it to friend, and friend would take it from him as well, okay. So during this communication, this guy doesn't need to know this state, okay, he wouldn't know. He's not going to open your parcel and see, oh, nice shoes, okay, he's not going to open your parcel. He wouldn't know what's inside, so he cannot determine this state, he cannot know this state, okay, by some measurement or something. If he tries to know this state, he would destroy it, so no copying like that, okay. Similarly, this guy, he would not know this state. I mean, he only knows that it's the state that that guy sent me, but he doesn't know the state, okay, and your friend wouldn't know it either unless he tries to perform some measurements, and if he performs a single measurement on this state, he doesn't know this state as well, okay. So I mean, he likes to hang this state on the wall or do something in some other computation, he needs this state, okay. So but he cannot know this state, okay, by performing some measurement. So during this communication, nobody knows what state this guy is sending, okay. Even this guy doesn't need to know his state, he only knows his qubit is in some state, of course, so he sent that parcel, okay. If it's nice shoes or bad shoes, no problem, he sends, he puts something in his packet and sends it, okay. So now you know what kind of resources you need, what's the structure of the whole thing, how it would be done, okay. Now I'll tell you exactly what this guy needs to do to know these numbers, and what this guy needs to do once he knows these numbers, okay. So the operations that this guy does and this guy does, okay. So now let me draw a diagram here. So this shows that this is a C0 gate, okay. So this is for C0 on these two qubits, and these two qubits, this is the qubit that you want to teleport. So okay, so this is the package. This is the qubit that's entangled with the qubit, the resource qubit that this office has, okay. So this is DHL's office in Islamabad, okay. So this is that other half, and this is the qubit that this one has. So this is and this is, okay. There is this operation, this is what this office does, DHL office, okay. And after this, he needs to perform a measurement in X basis, but he can avoid that by applying another gate here. So that gate is a H gate, and that H gate is on this qubit, I guess. So let's put it H. So it's a single qubit gate, and then he performs a measurement over here. Let's call it M, and let's call this M. And once he performs these measurements, these qubits are projected onto some states, and this could be anyone. And then that's the information out of these four first qubit, state of the first qubit. So this number is state of first qubit that this guy measures. This is the state of the second qubit. So everything is at the moment, everything that I'm talking about is done by this guy. So, and then he sends this information, and this double line shows that its information is classical information, is calling a texting, okay, taking his phone or whatever. And this single line shows that it's a quantum information, basically a quantum line and state of quantum system. And here once this guy gets something, now he will be performing something, and the thing that he will be performing, he might be performing operation X or Z or something else, and it depends on what he gets from here. Okay, so this thing is in Islamabad, this thing is in New York. Okay, now let's do the algebra and see what you can get and what information corresponds to what operations for this to get this state exactly the same as that. Okay, so let's start with this state, and this is our package. This is, so I'll be applying C naught by taking this as control qubit and taking the other entangled one qubit that's entangled as target. Okay, so C naught on by using this as control on the target qubit. Now target qubit, for the target qubit we need to choose some Bell state. So for different Bell state, instruction after this part that this guy needs to execute, they differ. Okay, so let's start with things that I know. So this Bell state, it's 0 0 plus 1 1 divided by square root 2, of course, for normalization. So let's assume that these two offices, they share this Bell state. So the first qubit is in here, the second is in there. So first in Islamabad, second is there. So they share an entangled qubit in entangled state. Okay, pair of qubit in entangled state in this Bell state. For this Bell state, now this is the first part. Let me write it like this. So with psi, here it's the first part, let's call it, and now 1. Okay, so that's the state for 3 qubits, 1 qubit that I need to parcel and this entangled. And for this, now I can write this as alpha 0 plus beta 1, and just need to focus on this at the moment. So let's take this part plus alpha 0 plus beta 1 and one part, and let's write that as well. So I need to perform the C naught on these two. I'm not doing any operation on this qubit that's not with me in here. That qubit is in New York. Okay, so nobody in this office can perform any operation on this anyway. So what operation I suggested? It's C naught. Okay, so what C naught would do is state changes the state. So basically C naught on this state, it would give us another state, and that state would be from here it's alpha 0 0 plus beta 1 and 1. Okay, and then this qubit in New York plus here it's alpha 0 1 plus beta 0 plus beta 1 and 1, and it flips it, so it becomes 1 0, and then this qubit in New York. Okay, now I have this state. Now after this I either make measurement along SX or I need to perform this H gate here. So what H would do is, and H is on the first qubit, this one. Now this 1 2 means 1 is control, 2 is target. So H1 means I'm applying it to H1 only, qubit 1 only. Now if we apply this, what I get is H changes 0 to 0 plus 1. Okay, so it changes it to 0 plus 1, and then this qubit and that qubit I'm writing it as 0 0. Okay, so this and that, and then plus beta, and 1 changes to 0 minus 1. Okay, with H, so I'm applying H. Okay, it becomes 0 minus 1, and then this 1 and this 0. Similarly, for this part, I have alpha, and 0 goes to 0 plus 1, 1 1 plus beta, and 1 goes to 0 minus 1, and then it's 0 and 1. Okay, now what, now let's remove this part. Now for first and second qubit, first and second, let's rearrange this state and write, if first and second is in 0, it's here and here, 0, and then it's here. Okay, so there are two parts where first qubit is in 0 0. So first two qubits in 0 0, and here it's alpha, and this third state 0, this is third, first, second, third now. Okay, and here it's plus beta and 1. That's one thing. Similarly, when it's 0 and 1, so now let's do 0 and 1. So let me write it here. 0 1 is here, 0 and 1. So it's no, here is 0 and 1. This is 0, this is 1. Okay, so it's beta, this 0 1, and then third qubit is in state 0, and then 0 and 1 here, plus alpha 1, this is 1. Now there are other possibilities as well, and these possibilities are 1 0 and 1 1 for the first two qubit. And for 1 0, this is 1, no, yes, this is first, this is 1, but it's now 0. This is 1, this is 1, so this is 1 and this is 0. Okay, so it's beta. This is 0. Which one? इसमें है. First one is 1. I'm talking about 1. So that's 1 and that's 0. Okay, but with minus sign. Okay, so it's minus beta, and the rest is 1. So minus beta 1, and what else we can get? 1 0. First term, yes, 1 0. So it's alpha plus alpha. Third state is 0. And with fourth, what do I have now? 1 1. So this is 1, this is 1. So it's minus beta, and third is 0. And then this is 1 1 plus alpha, and this is also 1. Okay. So I rewrote this like this. Now you can clearly see that if Islamabad office tries to measure the state of its qubits, so they have the 2 qubits now. So if they measure state of their qubits 1 and 2, they have these 4 possibilities. Okay. Suppose they perform measurement and they get something. Suppose they get 0 0. If they get 0 0, the state of the qubit in the New York would be alpha 0 plus beta 1. This is the same state that we started with. So that state is already transferred, and that office has nothing, that doesn't need to do anything with that. Okay, so they already got that state. So state is teleported. If he performs measurement, he gets 0 0, state is teleported. If Islamabad office performs a measurement and they get 0 1, then the New York office has this state. Now this state has these amplitudes flipped. So they need to flip it back. So they need to perform X, operation X. So here they need to perform identity, will do nothing. Here they need to perform X. It will, this X will make this state alpha 0 plus beta 1, original state, okay? And if this office measures and they get 1 0, then this is alpha 0, instead of plus beta 1, this has minus beta 1. So now they need to perform Z, because Z can flip the sign of the second. So this is Z. If they get this one, then they need to perform Z. And if this office gets this, then they need to perform Z and X. So basically XZ or ZX. Okay. So they perform X and they get alpha 0 minus beta 1 minus alpha 0 beta 1, and then they perform okay, let's maybe there is a maybe I mean there is a sign difference as well. Sign doesn't matter, but let's make it exactly the same. So pehle X, so X goes there, X0 plus beta 1. This sign stays the same, so they either need to, if they want the phase, then what they can do is they can maybe rotate it by 2 pi. So if you rotate a qubit, state of a qubit by 2 pi like this, then its sign changes actually, but it doesn't matter. So I mean here is up to sign. I mean it's a global phase. So if you do these operations, then you would get alpha 0 plus beta 1 minus, which is minus the original state. So this is a global phase. So if now this is Islamabad office, courier office, they perform their measurement, they get these 2 numbers, and these 2 numbers are now classical numbers, so either 0 or 1, classical bits. They text it or email it to their DHL office there, and that DHL office already knew that okay, if I get 0 0, I wouldn't do anything. If I get 0 1, then I would perform this operation, and so on. Okay, so they know how to do how to convert this state back to the original state without knowing the state. Okay, so they perform these measurements. So for 0 0 0 1 1 0 1 1, this office has to do these operations on the state. So 0 1, it's X, is Z, is ZX. Okay, once they do this, state is transferred up to a phase. Okay, so this is how a quantum state can be teleported. Now in this setup, no qubit physically moved from Islamabad to New York. Okay, only the state transferred, and the crucial role was the of the entanglement. If they did not have this entangled pair in the Bell state, they would not be able to transfer this state. Okay, so if you choose another Bell state, this dictionary would change accordingly. Okay, but it's always possible. For this kind of entangled state, you perform some operations and you do this. So this diagram is called a quantum circuit. Okay, it just symbolizes what to do, and it's for teleportation of a state. After these measurements, this guy will get this. So using entanglement and some quantum operations, quantum gates, we are able to transfer a state. And during this operation, we never copied this state. We never tried to, determine the state. Okay, we just, with full honesty, we take the package, we deliver it to other party. Okay. So, any question? How much time I have? Okay. Let me see. Okay, let me see if I have something else. Okay, anything related to this stuff? I mean, that you like to know? I'm not an expert in quantum computation or quantum information, but this is very basic stuff. You can go and read it in Nielsen and John. Yeah, it's chapter 1 is okay, and you can also go to chapter 2, and I mean you can know more, but chapter 1 is fine. Yes, thanks. That's a good question for this 5 or 10 minutes. So, to get Bell state formally using the mathematics, it's very easy. All you need to do is basically you need to have this and this operation. So if you start with 0, so let me show you. So you start with a state in 0 or 1 and you perform some operations and you'll get it in one of the Bell state. And I think I have it. Again, I pictured from Nielsen and Chuang. Yes. So in Nielsen and Chuang, this it's equation, maybe equation 1.27 or something below. You can read it more there, but I'll explain it to you here. So it's basically in this Hadamard gate, and it's called Hadamard gate and C0 gate. You perform these two operations, and what you do is, suppose you have, you need to have 2 qubits. Suppose you have in this state, you perform H on first one. So this is the circuit for this. This is H on first qubit, and this is Y on the other. So this is H, this is C0, and this C0, this is target, this is control. Okay, so you perform this, and this is your input, and here would be output. Suppose you have this state, you perform H on this, on the first, so H1, you get 0 minus 1 by square root 2 times 0. Now you perform this C0, and C0 would do from 0 0, it will give you 0 0, and from 1 0 it will give you 1 1. So you got this. This is one of the Bell state. It's entangled, you can see that. And if you start with another state, suppose you start with the 0, 1, then H1 will give you again 0 minus 1. No, it's H on H0, okay. And then C naught 1, 2, and this will give you from first one, it will give you 0, 1, plus from second one, it will give you 1, 0. Okay. So you can get this state from that. Similarly, if you had this one, now you can get 0, minus 1. There are two, so we don't need this one too. Okay. This is 0 here. So now C naught would give us 0, 0 minus 1, 1. We already made that, no?
Plus है sir, plus 1.
Which one?
Sir वो first जो आपने किया 0 0.
Oh, okay. So this H changes 0 to 0 plus. Okay, so this is plus. So here it changes 1 to 0 minus. Okay, so this is another, and from 1, 1, it's very easy. H1 will give us 0 minus 1. And C naught will give us 0, 1 minus 1, 0. So we obtain all 4 Bell state like that. Okay. The question is how to do this experimentally actually. I mean how to implement this C naught experimentally. For that, our Hamiltonian needs to have certain structure. Our Hamiltonian needs to have that structure that if our control qubit is in 0, it doesn't evolve the state, and if it's in state 1, then the Hamiltonian would actually have something to, and that would evolve the qubit state of the qubit too. So the Hamiltonian needs to have this kind of structure. So this is first qubit. Then I into, don't do anything, plus x into. So if our Hamiltonian has this kind of structure, then its evolution would do this conditionally, this conditional operation. Okay. And yeah. Yes, it is still mathematical. I mean, that's the challenge. For single qubit operations, it's very simple. Okay, so you simply just apply a field and monitor the evolution. But for 2 qubits, to entangle 2 qubits, you need to have an interaction between them. So in experimental setups, you always have some physical system that realizes these states of these qubits. So that physical system, whether it's a quantum spin of electron or something, or whether it's an atom, a state of an atom, for example, hyperfine levels or whatever, or maybe a state of superconducting squid. I mean, you need to couple it to the other qubit. physically. So that coupling can be realized in different ways for different kind of systems. I'm not an expert of that, but for simple spins, for example, we have dipole-dipole coupling, but that dipole-dipole coupling is simply like this. So it's a spin of first and spin of second, maybe ZZ or maybe full Heisenberg. It's called Heisenberg. Maybe like that. So spin-spin interaction. This could be quantum or just classical dipole-dipole interaction. Things like that are very easy, but I'm not sure how they do this conditional stuff. But I'm sure people do it all the time, so it must be simple. Okay, I only don't know because it's not my field actually. So otherwise it's very basic. Anyone working in this area would definitely know this. So the basic stuff is that you need to engineer a certain type of interaction between your qubits that would generate that entanglement over time via time evolution. Oh, okay. So what you usually do is, I mean, you generate that interaction locally and then you move your qubit to New York. So this DHL office, once they had both their qubits in one place and then they did this operation and prepared them in one of the Bell state and then they moved one qubit far away. Conceptually that simple, but experimentally I think with lasers and stuff, people I think maybe they can do they start their qubits over here and then they send with lasers. The qubits is basically polarization of your photon, so it can be either right circularly polarized or left circularly polarized, so it's like +1 and -1. So you create a pair of entangled photon using some nonlinear optical elements, and then you send one of your photon to the other party via some cable, fiber optic cable or something, and they have that, and after that you can transfer your state via this protocol. I mean, physically moving a photon from one place to another via optical cable, that's simple. Even this Wi-Fi, PTCL Wi-Fi, usually they have this flash fiber. So this is fiber optic. So it's not quantum, but the data is sent via optical connection. So with lasers and with single photons or photon packets, people I think routinely do this. With real systems, there are other problems actually. I mean, here we considered very clean system. They are not interacting with anything else. With real systems, our qubits would be interacting with the real world, with other things around, and those would destroy their state to a certain degree. Would create decoherence, what we call decoherence. Okay, their quantum interference ability to quantum interfere would be reduced. Plus, real measurements on real qubits, they would not be ideal as well. So those measurement operators and stuff, I mean, they are not 100% reliable sometime, and I think those also create certain problems. So experimental problems and challenges are a different set of objects. I mean, I'm not expert, I cannot talk about that. So thank you.
The paper that you talked about, I was looking at that. So it's 100 pixels that they have transmitted from one place to the other. But these are not qubits.
Okay.
These are continuous variables, and there is no the Hilbert space is infinite dimensional. So that, do
I
you know
think
it?
it's like zero, beta, alpha, and beta. I think.
No, there's no 0 and 1. It's there are no qubits over there.
Okay.
It's continuous variables. So
Okay.
it's like x and p.
Okay.
So somehow these states are entangled, but though that entanglement is again, it means the same thing, that you can't separate the state into tensor
Product.
parts, tensor products. But how they do it, I don't know.
Maybe every pixel corresponds to certain number, and that number is either this or that or something, or maybe like x and p. Yeah, I don't know either. I've never worked on any research problem, so my knowledge is very shallow in this regard.
Yeah, we should look it up. Maybe somebody will want to look it up and talk about it here.
Yeah, if anyone of you, I mean, have anyone, have you ever like worked on any quantum information or quantum computation problem? Anyone? At Kajazam University, some people take this course, quantum information and quantum computation. No one.
So apparently this is something that is not very new, but the technology is improved, and that's why they were able to send 100 at the same time. But I'd like to know how it works.
Yeah, maybe we invite some quantum computation guy. Any simple